Today I'm gonna talk about how to use optimization technique in the design of wind farms and the impact that this can have in practice. Um, in these slides, you see co-authors of mine that belongs to different paper that I will present in this presentation. And then at the very end of the presentation, you will also find references to the paper and also to some more recent work that I've done in the wind energy area. Let's say that my background it's in operations research, which is, let's say for the general public, let's say that is a field that we can say is between mathematics and computer science, as we like to use mathematical models, but also algorithms to solve optimization challenges. And in particular, I worked a lot in wind energy problems. So here already the presentation covered everything. I have an industrial PhD in in operations research. That was a collaboration between DTU and Vattenfall. So DTU is the Technical University of Denmark and Vattenfall is a lead energy company in North Europe. And the presentation that I'm gonna give today covers my industrial PhD, so it's material from that. And again, I will give them some more recent references. And after that, as I said, I worked in the same company for a few years as a lead engineer, where I was leading an operations research group. And our goal was to find new areas where to apply these techniques. Then I worked in a research center of a public institution, the European Commission. And finally, I followed my call of going back to academia. And now I'm a tenure track at the University of Seville. The project that I'm going to present as already, I will be very quick here, was very successful actually, because it had a big impact money-wise, as we're going to see in the presentation, but also the single problems weren't easy to solve. So it was also very interesting scientific-wise. And this gave us, I think, a unique angle that was very recognized. So I will start to talk about this optimization of wind farms. So I will start a little bit from the context around this project. So I was working for Vattenfall, that is this energy company. They have different kind of energies that they produce and sell, but I was focusing on wind energy. This is because the company in general wanted to focus always more on renewable energies, and they had this ambitious goal of saying we want to allow fossil-free living within one generation. So, okay, the company wanted to invest always more in renewables and in particular in wind energy. That is the area where I was working. But what does it mean investing in renewable? So for how is the system in Europe is not enough that the company says, look, I put bigger investments in this area and we become bigger, we strengthen this area. There is much more. And this is because the system of wind energy in Europe, especially offshore wind energy, that is where I focused, is based on tenders. So basically, each state in Europe can decide that a certain area will become a wind farm. The state selects the area and puts it on tender. Different companies like Vattenfall will enter this tender, proposing how they would construct the park and for how much they would sell the energy. The company that can build and operate a farm, asking for the lowest subsidies, will win the tender. So, for example, here we see an example from the Netherlands, where we have 4 areas on tenders. They were actually tendered in 2 different tenders. We had 1 and 2, and then in a second step, 3 and 4. And as I said, different company can enter this tender. The tender gives the area that is available, gives also the maximum production of the site. And this is because, of course, these wind farms will be connected to the grid and needs to operate properly with the energy systems already in place in the country. So this is also regulated. And then it's up to the company that wants to enter the bid to design how they want to build it. this market is becoming always more and more competitive. And so here it's really important to find innovative solutions to be able to win this competition. Notice also that there is a lot of works that goes into the bid itself. And so if a company doesn't win it, it doesn't capitalize on all of this investment, because basically companies like Vattenfall earn money by building and operating this park and selling the energy. So the main income is by selling the energy. So if you don't win the tender, you cannot construct and you cannot make that business. So among the different innovation projects that Vattenfall had internally, they also figure out that operations research was a good tool to be much more competitive in this area. So this is exactly the project we worked on. So let's say we started with the fact that operation research, when I started the PhD, hasn't been used before much in this area. And so our question was, our gamble was, can we use this technique in this application, and what was the impact it would make? And as we will see in the presentation, it can actually make a big impact. So to summarize the presentation, we're going to talk about two main design problems that are the wind farm layout problem and the cable routing. So if we see, let's say, the problem with an helicopter view, we have a given area on tender. This is, for example, a real world park where there was on tender the areas within the red boundaries. So the first problem is to decide where to locate the turbines in this site. And the second problem, where we used operations research, is how to connect the turbines with cables. So we're going to go through this step by step, and we will be part of this journey. So we start with the first one, that is the turbine layout optimization. That is the question of deciding where to place the turbines in this site. So here I show you a picture that is a real world wind farm. It's located in Denmark. And at the end of this presentation, when you're going to see a park like this, you will say, this is an old park. And why can you say that this is an old park? Because all the turbines are laid on a very regular grid. So this is very pretty to see. But what we know now is also that layout of this type are subject to a lot of wake effect. So wake effect is shown in this picture. This is a picture from the same wind park that I showed before in a specific wind condition, where you see that the first line of turbines are hit by full wind, while all the turbines in the back are in the shade of the previous one. So what does it mean? That the first line of turbine can produce the maximum that that type of turbine could produce in that wind scenario. But all the other in the back, they face less wind and actually also higher turbulence, and so they cannot produce as much. So the aerodynamic idea is very similar of when you see biking competition or if you do sailing. When you bike, you always try to stay in the shade of another cyclist so that you are hit by less wind, right? The concept is exactly the same, but for turbines, you want the opposite. You want to be hit by the highest wind you can, because then you can produce more. So in this specific wind scenario that we are seeing in the picture, if any of these turbines in the back was placed a little bit more to the right or a little bit more to the left, it would have less wake effect, and then the overall production of the park would be higher. So basically we started with this, like how can we place turbines in a site to minimize the wake effect? So to summarize, we have a certain area given on tender, and we have a number of turbines that we want to place in this area. So the number of turbines is usually selected by the engineers in the company. Basically, as I explained before, in the tender, they give us what can be the maximum production of the site. Then the engineers decide for the specific type of turbine that they want to use in the park. And this basically defines how many turbines they want to place. We also get from tender a lot of information about the wind statistics in the site, the soil condition, etc. So our goal at the moment is, given this area, given the number of turbine and the type of turbines that the company wants to put, decide where to place them in the site. And the goal is to maximize production, or in another way, minimizing this wake effect. Another time, the business of the company is to sell energy. So maximizing production means maximizing profit. In reality, there is also a cost aspect related to the layout that when we started this project wasn't explicitly considered in the company. And now I will explain this sentence in more details. So the fact is that depending on the water depth and the soil condition, you may need different type of foundations depending on where you place the turbine. So you could say that it is a balance between maximizing production and minimizing the location costs. So in the time when I worked on this at the company, they had some commercial software to optimize the turbine location based on maximizing production. And then for deciding how to reduce the cost, they were basically analyzing the cost of building each of the specific turbine in the layout selected and then moving them manually. We instead wanted to insert this immediately in the optimization. And so we proposed to the company, if you could give us a cost map that represents basically for each possible position, what would be the cost of building a turbine there, we can incorporate this explicitly in the optimization. And as we will see later in the results, this also has a significant impact. Let's say that from a company perspective, this is also very interesting because I don't know, sometimes if we are from academia, we don't see this aspect. It seems pretty logical, but in the company it was very interesting because it changed the process compared of how it was done before. And I have to say that the company was really open on to find innovation, etc. And so they develop a tool that or perfectionize a tool for defining this cost map. So now we change a bit the process and we have this cost map for each of the possible positions. So then we started to work with mathematics. So we said, okay, how do we solve this problem? And as a good operational researcher, we like to write mathematical models as the first approach. So what we did was to discretize the available area in a number of possible positions. And for each of these positions, we have a binary variable that is equal to 1 if I build a turbine in this site, or 0 otherwise. We can then write the problem as I explained it to you with a mathematical model. So here I will go a little bit fast maybe, but the idea is that in our objective function, we want to maximize PI, that is the power production, including the interference that is here represented by WI, and considering also the cost of foundations. The constraint that we have are, the first one relates to the number of turbines that we can place in the site. The third one basically encodes how to compute the interference or how to include it in the model. And the second one is an incompatibility constraint. So this one I haven't mentioned, but actually when you place turbines in a site, you cannot place them too close to each other because otherwise the blades would clash. So in practice, the company would give us a minimum distance that they want for the turbines, and we would include it in the model with this constraint that basically says that if two turbines are too close to each other, they are incompatible, as I say here in the model, I cannot place them both. This model was new compared to there were some models in the literature, but our formulation was different than the one in the literature. And this, for people that are not from operations research, can give very different results. So even if you model the same reality, let's say, but with two different models, you can get better, let's say, performances. And so this was the case of our model that, as it is, was able to solve instances of about 1,000 possible positions compared to the literature ones that were able to solve about 100 possible positions, talking about mathematical models. Another big advantage of using our formulation is that the way we compute interference scales very well in a stochastic programming variant. So let's start to, first of all, say why do we talk about stochasticity? Well, if we optimize the position of the turbines to minimize wake effect, we have to be careful of the wind. So if we only look at the main wind direction, we may end up in the situation that we have seen in the picture. So it's a layout that is very good for the main wind condition, but as soon as the wind changes, may have very high interference. So I don't know if you can see my hands, but one example would be if I place two turbines like my hands and the wind is blowing in this direction, this is an optimal layout. But if the wind blows in this direction, then it's the worst layout I could find. So in this sense, it's very important to consider the full variability of wind. And in the company setting, we were talking about 100,000 of possible wind scenarios in practice. So the advantage of using this our mathematical model, the mathematical model I presented before, is that we can encapsulate this one in a pre-processing step. So basically, if you develop the stochastic programming variant of the previous model, you will see that reduce into calculating in an interference matrix that doesn't consider only one cone of interference, but consider the weighted average of all the possible ones. So in easy words, what our software or our model sees is not a single cone of interference, but is kind of a star of interference computed on a very large number of wind scenarios. So we were very happy, right? We had a model that at least compared to the literature was working very well. So we went to the company and said, okay, we are ready to test this, give us some real instances. And we were faced with instances with more than 20,000 possible positions. So as I said, we were really proud of our 1,000 possible solving instances with about 1,000 possible positions. And we realized that working in practice, we were working on a completely different scale. And so here is where we had to go back to our office and work again on this. And in particular, we worked on using a technique that we call a set of techniques called math heuristics. So math heuristics is kind of a combination of mathematical models and heuristic. So let's say, generally speaking, the idea is to use the MIP solver that are solvers that we use to solve the mathematical model in a heuristic way. So in particular, for this specific problem, we used MIP-based heuristic, so a math heuristic that is called proximity search. So this already existed in the literature, but was never used for this application and proved to work very well. So since the audience could be mixed, I will not go in a lot of details here, but I added here a reference, so in the paper you can find all the detail. Let's say that the general idea is that given a heuristic solution, we explore the neighborhood of this solution using the MIP solver itself. So basically, you will see on the problem that we act on our mathematical model to in this heuristic setting, let's say. So let's see a little bit the results. So here you see the results on two different instances. So on the left, you have an instance of about 5,000 possible positions, and on the right, one of about 10,000 possible positions. So we are comparing, so we have on the x-axis time, so we want, of course, to be as fast as possible in the resolution of our problem. And on the y-axis, we have profit. So we want to be as high as possible because we want the highest possible profit. We are comparing our methodology that is here indicated in black as proximity search against purely mathematical models and that are in green and red, and purely heuristic methods, for example, your local search that is represented in blue. So for the SIP, for the mathematical models, you have two options, the green and the red, because basically we use the Cplex, that is a solver for mathematical models, in the default setting in the green, and with some more pushed, let's say, heuristic setting in the red one. So what you can see in these two plots is that our method outperforms the competitors as it is faster and it can also reach better solutions. So now we went back to the company and we say, okay, now we think we are ready for testing this in practice. And in the company, indeed, we did the full validation of this software. Here I show you a real world case on which we did one of the different tests of the validation. So you see the available area is represented in green. And what you can notice here is also that not all the area was available for building a park. So you can see that there is kind of a white cross in the middle. In this case, it was because in the middle of the site, there were two huge export cables. So you cannot build turbines on top of the cables. So this means simply that this area is not available for building turbines. Since we used a discrete method, we discretized the site. For us, it's very easy to consider this in the optimization because simply we don't put possible positions in there, and that's it. So we have, as I said, the green area is where we can place turbines. At the same time, in this site, they have very complex soil conditions. So they have different water depths and different condition of the bottom of the sea. So the result is that there were positions that were much more expensive to build on. These are the red one, and the blue ones that were cheaper. So I cannot show the numbers here for privacy reason, but the main concept is this one. We had to balance between a position that had possibly higher production and possibly also a higher cost compared to others. So we are given this information in input and together with the number of turbines that we want to place. So we optimize the layout and we obtain the black layout here. So the dots represent turbines. And we compare this one with the layout that would have been done otherwise inside the company, that is represented in pink. So as I mentioned already, the company had a commercial software to optimize the layout based on production. And they couldn't consider explicitly the cost of foundations in the optimization. So what they were doing was optimizing on production, then calculate how much was the cost for building these turbines. And if it was very expensive, they were manually changing them. So this is why in this slide, I call it a manual layout, the pink one, even if it's actually a combination between a software and a manual adjustment. When we had both the layouts, the one we developed again in black and the one done by the company in pink, we give them both to a third team that had advanced simulation software that basically simulates in details the aerodynamic in the site and the wake effect. They came back from this independent analysis saying that our layout was not only allowing a higher production compared to the pink one, so the company one, but was also much cheaper at construction time due to the cost of foundation. So they estimated that using our layout compared to the one that the company would have otherwise developed would have implied a gain of about $14.2 million in the lifetime of the park. And what is fascinating of this is that this is achieved simply by putting turbines in a slightly different position, which though is not trivial to find without advanced operational research. Now you could tell me, okay, Martina, but I think that this comparison, it's very relevant from a company perspective, but you're not fully comparing apples to apples because you are comparing a tool where you can consider cost of foundation with a tool where you cannot include cost of foundations. So we did another test. So in this case, the cost of foundations were really relevant because the sea bottom was very flat and homogeneous. So in this case, it wasn't relevant to consider cost of foundation. So here we are focusing only on optimized power production. You can see again here in green the available area. Also here you can see that there are some areas where we cannot place turbines, so it's not a continuous area, but that's not a problem to us. In this plot, you can see also a lot of other dots that are outside the green area. These are already existing wind farms that were in the area. It is very important for us to consider these turbines because even if we cannot change them because they are already constructed and built, these turbines will have an impact on our turbines because they also generate wake effect on us. So when we optimize our wind farm, we have to consider also the wake effect from these turbines. So one thing you can notice, for example, I hope you can see my mouse, I'm not sure, but in this top part close to the black dots, you can see that the turbines don't go exactly on the edge of the available area, and this is because they are suffering the wake effect from the black turbines. So, okay, now we have all the explained, let's say, the input of our problem, and we optimize the layout using our software that is giving the layout in red, and compared it with one of the commercial software used by the company in blue. So again, these two layouts were given to an independent software that computed the difference in production, and they estimated that using our layout instead of the blue one, the red one instead of the blue one, the company could earn about $11.5 million in the lifetime of the park. So this, of course, was the company was very happy of these results and started to utilize this software in practice. They built up a team also to construct more layers and business cases around this. And this software has been routinely used in the company to design wind farms. In particular, a case that we are really proud of is the one that I show in this picture that is the first one I show you at the beginning, the plot when I was saying this area is from the Netherlands, when I was talking about competition. And we are particularly proud of this layout because Vattenfall won this tender using our operation research tools, among, of course, others. And this is a key site because it was the first site where they bidded subsidy free. So it was the first site actually that was constructed subsidy free. So this shows that really this innovation in the business are really pushing the business forward. And this is also very important from, a sustainability perspective because it's making wind energy more competitive compared to other sources of energy. So this leads us to the second part of the talk that regards the cable routing optimization, that is the challenge of connecting turbines with cables. So now we have we have located the turbines in the site and we want to transport their energy from the turbines to shore. So here the challenge is how do we connect these turbines to do this? In practice, what happens in reality is that in offshore wind parks, you have what is called an offshore substation that you see here in the picture on the left, which is a structure where all the energy from the turbine is collected. And basically the main goal of this structure is to change the voltage from what they are called the inter-array cables, that are the cables that connect the turbines, to a huge export cable that then connects the substation to the grid onshore. So in our case, we were focusing on the connection among the turbines and the offshore substation. So this is the setting we had. We have the layout optimization. So we have the layout of the turbines done, finished, and we have the position of the substation that is here represented. This is the setting that we worked on because it was the setting that happened most of the time for the company. So usually the substation is built by the grid operator and instead the internal cables routing is built by the company. So in our setting, the interest was focusing on this situation, and this is what I'm gonna present today, and then I'm giving you some references later on other possibilities. So again, we have the turbines, we have the substation, and we have to connect them with cables. So what we realize is that this is actually a problem on a graph, where our turbines are the nodes of this graph, and the substation is the root of this arborescence. we have different kind of cables with which we can connect these turbines that here are represented with different colors. So we want all the turbines to be connected to the substation, and we can do this connection using different kind of cables. Different kind of cables are characterized by a different cost and a different capacity. So capacity is how much current can pass through the cable. And of course, the more current, the bigger the cable, the more expensive it is. So it is an optimization challenge to decide how to connect them and also what kind of cable to use. So as I mentioned, this was a problem on a graph. So we, as operation researcher, like to write mathematical models, and we wrote a mathematical model on the graph. In particular, in this model, we have variables on the arcs that are the flow, that represent the current passing through, the electrical current passing through the cable. And then we have a binary variable, xijt, that tells me if I build an arc of type t between I and j. We also have a supporting variable yij that just tells me if there is a direct connection between I and j. This problem has also, in practice, a lot of limitations that we had to consider in our optimization. So the first one is that only one cable can exit a turbine. So this has to do with the physical connection at the turbine. So at the base of the turbine, there are kind of some plugs, and you can plug more cables in the turbine, but only one can leave the turbine. So in this graph, you can see there are some structure right here in the turbine 51, where you can see two cables. The green one enter the turbine and the purple one exit, so only one exits. Let's say exiting is in the direction of the substation, while entering, let's say, is the opposite direction. And the flow of the current, of course, moves from the turbines, here represented like the black dots, to the substation, that is the red square. As we said, we have different cable types, and each of them has a given capacity. So for example, here that we show in this feasible solution, the purple one is the cable that has the highest capacity, so can handle the current of more turbines, and is also the more expensive one. Another constraint that was quite difficult to handle in let's say, in our operations research mathematical model was the cable crossings. So basically, in theory, cables could cross. So basically, you can have a cable and then lay another one on top, but at the cost of having a very expensive isolating system between the two, so not to have magnetic interference between the cables. So this structure is very expensive, but on top is also very risky, because there is a high risk that when you lay the top cable, you would break the second cable. And this then implies huge cost for fixing it. So the general rule from the company is we want to avoid cable crossing. Of course, using our model, we could also test this hypothesis, like we can generate solution with crossing and solution without crossing, evaluate their cost, and let the experts decide. But it's true that is a good rule of thumb to not have cable crossing, and this in practice was always the solution preferred by the company to avoid risks. So as you can see, for example, in this graph that I'm showing here on the left, this is a feasible solution as we do not have any cable crossing. Another limitation that we had to consider was obstacles in the site. So there could be physical things that are present on the site. These could be other wind farms that are already existing there, natural reserves. Sometimes we even found the airplane from World War II that were in the bottom of the sea. So these are all, let's say, defined areas that cannot be crossed by the cables. So here in the plot, you see these black polygons represent possible obstacles, and the solution that you see is feasible because avoids them. Finally, there are also some limitation at the substation, because also the substation physically is as a number of plugs, let's say. So there is a maximum number of connection to the substation. So the number of cables that connects here to the red square is limited and given in input. So these are the limitations of the main the main settings for the problem. Another interesting thing that we considered in our work was cable losses. So basically, when you have a cable, the cable has an intrinsic resistance in it. So when the current passes through, part of the current gets lost because of this resistance of the cable. This phenomenon implies, of course, that you lose some of your production, and so you also lose some money. What is interesting is that different cable types have also different resistances. So usually the more expensive cables have also lower resistance. So something that the electrical engineers in the company really wanted to challenge and discover was where was the balance. So would it make sense to buy more expensive cables, so have a higher capex cost or immediate cost in order to save on losses in the lifetime of the park? And we could include this one directly in the optimization, and so answer this question, showing also how this would change the layout, so the connection with the turbines. So we're going to see this later on in the results. So maybe here I will go a bit faster, but as before, we like to write mathematical models. So everything I explained you so far, we wrote it down in a mathematical model. Where we had some challenges was with the no crossing constraint. This is because in input, the optimization model sees the complete graph, so sees all the possible connections between all the turbines. So this means that there are a lot of possible crossings, and so the model was becoming very heavy because it had a lot of non-crossing constraints. So the approach we used here was to add these non-crossing constraints on the fly. So for the people that are from operation research background, basically we use a callback from Cplex. Every time we were getting a solution, we were checking if there were crossings, and we were adding to the model only the crossing that were actually found. And this proved to be very effective because in the end there weren't that many in the solution, but potentially there were many in the input graph. Also in this case, everything was working well in theory, but then when we went to talk to the company, we realized that indeed in practice they had a lot of turbines, so especially in big sites with a lot of turbine, it was very challenging for the mathematical model to even find a first feasible solution. So it was spending a lot of time at the root node. So at this point, again, we decided to use a math heuristic approach. So again, a combination of mathematical models and heuristics, but a bit different from the previous one. So basically what we noticed here was that the challenge was even to find the first feasible solution. So our solution was to first relax the model and say to the MIP solver, look, you find me the first solution that you can, and I don't mind if it's disconnected. So we relax the model saying it's okay to have disconnected solution, even if of course we put a very high cost on them. And as soon as we were getting a solution, what we were doing was to fix some marks in this solution and tell to the optimizer, re-optimize with this fixed, and you are free to use the other one. So in this way, we were at each step reducing the size of the problem. And we iterated this until we get to a certain number of iterations, and then we were warm starting the original model, considering this solution, and letting it get to the optimality. So here in the video, you see, for example, an example of solution. You see that we start from disconnected solution that are expensive, and then we get to connected solutions. So actually solutions that are feasible and optimal for the original problem. And this proved to be very, very effective in reality. So somehow we are guiding the optimization tool. We are guiding heuristically the optimization tool. And this allowed us to find solutions also for very big instances. And now let's go to some practical results to see the impact in practice of using this optimization tool. So here, what was interesting is that there was no commercial tool to do the optimization of cable routing. So this was done manually. Basically, electrical engineers with pen and paper were given the positions of the turbines, and they have to decide how to connect them with cable. So here you see a real world park, which, as you can see, is old because all the turbines are very regular. And for this one, we had the layout that was chosen or designed by the manual operator. So you can see that there are 3 different type of cable. In blue on the top, you have the more expensive cable that can handle also the current from more turbine, in this case 16. Then you have the green one that is somehow the intermediate one. And at the very end, you have the black line that is the smallest cable that can support the current from only one turbine, but is also the cheapest one. You can see that the layout is very pretty, is very regular, and it was done by a human. Then we took exactly the same input and we said to our tool, okay, let's see what you can do. And this is the result we got. So you can see that is less regular, maybe less pretty than the manual one, but is also much cheaper than the one proposed by the company, let's say. In particular, using this layout, this cable layout compared to the previous one, the company could save $1.7 million. As I mentioned, we also worked on the idea of what would be the impact of considering cable losses. So here we are talking about CapEx, which means immediate costs, so the immediate cost that they pay for the cables. And if we instead consider also long-term costs that are related with the cable losses, this is the layout we obtain. So what we can notice is that considering cable losses is not taking the same layout and putting bigger cables. It really implies having a different layout because the costs are different. And you can see that the layout is somehow similar, but somehow also different. It's very different from the manual one. And if we compare it with the manual one, we can see that even this one optimized on both capex and losses is much cheaper at construction time, basically more or less the same, $1.7 million cheaper, and is also $1.9 million cheaper in the lifetime of the park because it reduced these cable losses. This was very interesting from the company, and something that they also loved about using these optimization tools is that they could try a lot of options. Imagine indeed that before with a manual operator, you could have a lot of questions that wasn't easy to solve or quantify the impact of choices, while having a tool like this one that can quickly give you a solution really opened up experimentation phase in the company. So we also implemented different options in our tool. So here I'm showing some of them. For example, the first layout here, it shows the problem as I explained it to you. In the second layout, in the second one, we started to talk about the cost for branches. So basically, in this layout, you can see we have structure, for example, in turbine number 5, where 2 cables enter a turbine and 1 exit. This is feasible, but can imply extra costs. So a lot of time in the company, they were pushing for what they call a string layout. So a layout where there was only one turbine connected to one turbine and no branches. So we have a version of the software that does that. So you can impose to only have strings and you can compare the costs. You can also do more. You can, and this is what we see in the middle, you can quantify what would be the cost of having branches, then give this in input to our optimizer that will decide, that will optimize based on also this cost and suggest you a layout. So for example, in this case, if we consider explicitly the cost for branches, we obtain this result where some branches still make sense to have and some other instead are lost. So for example, in turbine number 5 that we were looking at before, here it prefers to do a string structure, but in number 3 it still prefers to do a branching. Another option that we consider that is the right one is loops. So here you can see you have a string connection, meaning there are no branching, one turbine connected to one. And in addition, you want that the strings pairs in two to have this orange redundancy cable. And this is basically in case of broken cables, you ensure that all the turbines that are at all time connected to electricity. So this is a safety measure in case of let's say more risk adverse layout. And what was very cool from the company perspective is that we could obtain this layout, we could put prices on them, and so they could enter meetings with numbers and saying, okay, do we take this risk considering that we would have to pay this more in cables or not? And this lead them to have much more informed decisions. So next, I'm gonna show you a video. Please let me know if there are problems if you don't hear the audio, and we can fix it. And so this is a video where we basically recorded some testimonials from the company that use the software I explained in this presentation, and they give us their feedback.
I'm Thomas Hjort. I'm heading the system design department in Vattenfall's offshore wind division. I had the pleasure 3 years back of encountering a master's student in mathematics, working on something as strange as operational research, something I didn't know anything about. And when I saw it applied after the master's student project, when I saw it applied to the wind farm layout as a whole, it really became an interesting journey to be part of. We decided to create a small department that works on modeling an entire wind farm and thereby be able to explore different ways of designing the farm in very short time and with high benefit for our business cases.
In system design, we design the wind farms of the future. The optimizers are now fully integrated in our way of working, so we basically use it for all the wind farms that we design. For me personally, it is really cool to be able to work with these state-of-the-art models because I know it gives me the best tools to design the most competitive offshore wind farm. It's also tools like these that I know then that give me the edge over my competitors. And for the industry as a whole, it's of course very important, these innovations that drive down the costs, because that is what will enable offshore wind energy to be a key part of a greener energy system. The optimizers and the model framework in general basically triggered a new way of working in Vattenfall, because it allows us to quantify many different options that we consider for the offshore wind farms. And because of that, we don't only can rely on experience, but we can actually put numbers to all the different options that we want to consider.
Hey, I'm Magnus Hall, President and CEO of Vattenfall. The optimization software is now fully deployed and all our offshore wind farms are designed using these tools. Thanks to them, we can achieve better layouts in significantly less time, which allows us to experiment with more options and take more informed decisions. This kind of innovative solutions are of key importance for Vattenfall's wind business to be successful, but also to deliver on our purpose to enable fossil-free living within one generation.
Okay, I finished my presentation leaving some references. So here are the main papers that I explained in this presentation. This is also a paper that kind of wrap up the impact of using these tools in practice. And I also mentioned some related work that I didn't have time to go through in this presentation, but we also have a paper on the integrated problem, so putting together layout and cable routing, and also another paper on using machine learning together with operations research, in case, let's say, the area would not be defined and you have a lot of possible options of many possible sites and you have to decide. We use decide among them. We use the power of machine learning together with operation research to help in this decision. After this, I also worked on other problems related with wind energy. In particular, we have a paper related to the construction of offshore wind farms, which is also a big logistical challenge, as you can have an idea from this video. So here you find a reference to this paper. And the more recent work I worked on, this is now submitted to an international journal, is using again a mix of operation research and machine learning for the prevention of faults in wind farms. So in particular, we use counterfactual optimization, operation research actually in counterfactual optimization for designing controllers for wind farms. This ends my presentation, and I would like to thank you.